So this is lecture 7 of Python, and today we're going to talk about numerical integration and solving ordinary differential equations. If you've noticed, the focus of this mini course is rather numerical things that you can do in Python, and so this is no exception. But these are some common things that happen that you might have to do if you have numerical data. We're going to look at numerical integration, some ordinary differential equations. I'll give some examples. A bit of theory, but not too much on how to do this in Python. So numerical integration first. So suppose we have some function that is a function of two variables, x and y, and if I plot it 3D, it has some z component. And suppose I want to know what the volume is under this surface. Well, that is an integral. Where you integrate this function f, where x should be have two components, and that gives us the answer. So this is not uncommon. You have some data, you want to know the total of something, and so if this is the task that you're given, how would you go about doing that? And it depends. It turns out quite a bit on how many variables this function depends on. So if you have some function that describes f, and it depends on one variable, there's a whole host of very nice techniques you can use to get very accurate results. Whereas if d is very large, all of these turn out not to work. And the intermediate ranges are where you can sometimes get away with these tricks and sometimes not. So for d equals 1, so that's the dimension or the number of variables that your function depends on, you can do simple things like make a regular grid at which you evaluate your function and use those function values as in some way to approximate the integral. You can do a non-regular grid to optimize the error. So we'll see how that goes. And you can still do that when the number of integrals that you have is small, the number of dimensions is small, because you can think of computing this volume in a way where you just first compute the area in different slabs and just add those areas. So you can do it recursively. And that works okay if you don't have to do that recursion too deeply. So 2 or 3 is still doable. But if you had, I don't know, 2,000 variables that this function depends on, then that doesn't work. And such cases do occur if you, for instance, wanted to sample all configurations of a set of molecules, for instance, then that's the kind of space you'd have. You have 1,000 molecules, you have 1,000 dimensions, actually 1,000 times 3 if it's 3D. So having a lot of dimensions is not uncommon. But having few dimensions is also not uncommon. So we'll look at both possibilities, but depending on your dimension, what is a suitable approach differs. So let's look at 1D first, and let's look at a function f of x that gives us y values, and we want the area of a curve between a and b. So if you do that numerically, you could remember it's a function, right? It's a prescription that says if I have x, what would y be? But I don't have all of those points available. I have to evaluate them, right? And so the integral involves all possible functions, which is an infinite number of them, and we can obviously not do that. So we need to have a finite number. We have to discretize this somehow for it to be numerically feasible. And so a simple way to do that is to compute all the values y at equally spaced values of x. And then if we have those, we can sort of approximate the function in between. So you can do something like this. So if here's our function of f, and a and b are here, I could just evaluate it at these greenish-blue points and say, well, in between there, let's suppose that the function is linear. And you do that because if you assume that you can evaluate exactly what the area is, that is sort of this triangle plus a square. So I only need to know those 2 points to approximate them. But it's an approximation, right? So doing this linear interpolation is called the trapezoidal rule. And what you get is this shaded area. You don't get the actual answer, but there's no way to get the actual answer except by doing this ever more finely and seeing if you're getting close to the, or if the result is changing less and less. There's no way around it. There is a truncation error or a discretization error here. because we don't have the luxury of evaluating all points. If we could probably do this exactly, and we don't have to do this. But so the trapezoidal rule in sort of function or in mathematical forms, what you're doing is essentially so y1 is evaluated at x1, y2 at x2, etc. So those are the values of the function. You sum them up in some sort of nice way where you have extra factors of 1/2 at the endpoints. That's because you have these slanted triangle points. So for instance, if we wanted to do the integral from 0 to 10 of cosine x over 9 times sine squared x for no particular reason, then in Python we could code that in by having that function be defined by the def at return, etc. Setting some of the points and creating a linspace. So linspace did this nice uniform grid for us. So NumPy helps us out here. This is supposed to be running in IPython. So NumPy is already loaded. So 40 points, and I have to evaluate what the difference is between subsequent points. So by grid spacing, evaluate all of the functions fy. I'm secretly using a nice feature of NumPy here that sine and cosine are defined in NumPy to act on the whole array of x values at the same time and give you an array of those sine values. So this works because x here is a NumPy array, and cosine and x over 9 is a NumPy array with every element over 9, and cosine is the cosine of every element. So this element-wise stuff, I'm using that here. So this is a whole array operation, and then I'm going to basically evaluate this function by saying, okay, I take the sum of everything from all of the values except for the endpoints. The endpoints have to have a factor of 2 according to the formula, and I have to multiply the whole thing by dx, and that gives me the result. So I could see by increasing this number of points from 40 to 80 to 160 to see if I'm converging to some sort of result. But this gives me the approximation. So you can do this by hand, especially for these sort of simple equally spaced things. This is not too hard to do. You'd still use NumPy to get this done fairly fast. So that's an evenly spaced approach where you basically use a linspace. So that's essentially what we did with the trapezoidal rule. And these are based on this approximation of a linear function, right? So what you're really doing is for each of these intervals, you're making this kind of an approximation. You'd say your interval is a width h, and you take from point A to A plus h this interval, evaluating it at A and at A plus h, so those 2 points. And because it's so essentially the h over 2 comes from the linear interpolation. Now you don't have to do a linear interpolation. You can do something better if you use more points. So with 2 points, I can draw a straight line. If I had 3 points, I can make a quadratic approximation through that. And by doing higher and higher order approximations using more information of the points, I could get a more accurate interpolation. That is to say, the part of the function that I don't evaluate would be approximated better. And so one way to do that is Simpson's rule, which gives you essentially some funny prefactors that come out of the math of doing this approximation. Note that it's kind of funny the way it's written here because I'm taking twice the interval. It doesn't really matter, but that's what's happening here. So what happens to these little intervals is they don't get added on. And so you're reusing some of these points in the next interval because the third point becomes the second point of the next interval, etc. So you wrap that together into the equation that we saw in the previous slide. There's a whole slew of different ways of doing this, just different approximations to the points that you did not evaluate. I'm not going to go into every one of them. But they have different orders, and that means they converge more rapidly or less rapidly as you decrease the spacing. They might take different points in between, etc., etc. So it's all variations on a theme, right? You just take some points on the interval, you approximate your function in between with something that you then know, and you compute what the integral will be of that approximation. So these were all equally spaced points, you don't have to do that. You basically do that because you have no better reason to choose your points, right? If you don't know your function, that's sort of your best bet. It turns out it's not your best bet necessarily. There's ways of positioning the points at which you evaluate the function such that the error tends to be smaller. And this is done by just a different way of approximating your function. So rather than saying linear or curve, you use what's called orthogonal polynomials. So polynomials are a combination of powers, and you can find sets of them that can be used to approximate your function. So there'll typically be a constant, a linear, a quadratic, but they're not pure quadratics. They're some combination. So there's different families, Legendre, Chebyshev. You don't really have to know what they are, just that's what lies underneath. And then what you do with these approximations is that because you're taking a different sort of basis of how you approximate your functions, it turns out that there's better points you can choose to figure out what the coefficients are. So depending on what set you choose, and you won't choose it and you won't have to do this, but this is baked into the numerical recipes that you will use, you'll get a set of points xi in your interval that are chosen such that you get the best possible approximation. It's not an iterative thing. It depends on exactly the polynomials. It has something to do with the zeros of the polynomials, but again, the routine will take these points. They won't be regular space, but it will be sort of covering the interval nonetheless. Use that to construct an approximation of your function and integrate that function. But since we're just computing f at those values, at the end of the day, it's still just a weighted sum of all of these functions. So since I don't want to go into the theory of how you get the weights bi and the exact point, all you have to know is these functions evaluate your function, or these methods evaluate your functions at a finite number of points. They're not equally spaced. They're chosen very well, and the bi's are just chosen such that everything works out to be an approximation of your integral. And it tends to be more accurate. You did this for a reason. It tends to be more accurate than the equally spaced ones. So since you don't want to do this by hand, or even want to look up what those xi should be for every method, you want this to be already programmed in, and it is. So in Python, in SciPy, we have a sub-package called integrate, and one of the things that it has is something called fixed quad. So quadrature is the name of doing integration in this way, Gaussian quadrature. And fixed quad gives you essentially, I think it's using Legendre polynomials. You'd have to look that up, but you give it a function that we had already defined, beginning and end, and how many points you want to take. So how many what the n is the number of points. This is an approximation. It uses, I think, at least that many points, because it turns out that this doesn't work for arbitrary n. There's fixed numbers of n that work well for this. But it will take at least that many points and then return you the integral. It actually will return the integral and the error, but the integral is the element 0, so that's why if you print that, you get that. That's it. So the answer is very close to what we had before. It was something like 3.9 as well. It's probably a little bit more accurate. Yeah. So this is what it does, and the reason you use it is it is more accurate. Although the other thing was easier to understand because you kind of see what's happening. This is what's happening behind the scenes in fixed quad. So now the question is, was this accurate? We know it's an approximation. Knowing that it is an approximation, we shouldn't be satisfied until we know how good an approximation it is, right? If you can't say, well, it's good within plus or minus 3, and if the value is 3, that's like, what is our error? And so we know that more points give us a better approximation, but this depends on how smooth our function is, and we do not know that beforehand. So what we should really have, rather than saying, give me 40 points, we should say, well, keep increasing the number of points until your value has converged within a certain tolerance. And so that's an adaptive integration where you keep adding points until the end result doesn't change. Now, that doesn't necessarily guarantee it's the right answer. It is possible that where we chose our points just happens to miss a really important region where a lot of things in the function change, but adding more points, we didn't hit that region. So it's not guaranteed to give it, but if it doesn't reach sort of a steady state, like a steady value after increasing the number of points, if it doesn't do that, you're sure that it's not right. Okay, so this is sort of a lower bound on your accuracy. So again, you could do this by hand by increasing n and checking if the value is closer to the previous value than a certain tolerance. Or you can just use SciPy again. It's the same SciPy integrate has a thing called quad rather than quad fixed, which is sort of the natural routine you really use. And you specify an epsilon, so a tolerance to how good an approximation this should be. So you can ask it to compute this integral up to 10 to the minus 3, relatively speaking. And so it'll do that, and it'll try and go on until the error, and the error, of course, being determined by one approximation versus the next with an increased number of points, is less than that value. So when I print I3, this time I'm not just printing the value, but also the estimated error. And that error is indeed less than 10 to the minus 3. The smaller you make that, the more function evaluation will be necessary. And so the more expensive it is. So if you don't need it that accurate, if you only need it accurate up to 10%, then you say 0.1, it'll be faster. Now for one single function, that's not going to matter much, but say you have to do this a million times, then it starts to matter. So you can say relative errors, but you can also specify to have an absolute tolerance. That's especially good if you suspect that your result might be close to 0 or should be exactly 0. Asking for a relative error of 10 to the minus 3 when your result is going to be 0 will just never converge, because it'll compute whatever error it has, divide by 0, and get infinity and say, I'm not converged, and it'll keep on going forever. You can also give a limit to the number of subintervals to use so that you don't go on forever, at least it stops at some point. And then since it returns the error, you can always check if things were properly found, if the integral is properly evaluated. So that's 1D error, 1D integration. There's a function for it in Python in SciPy because it's a common thing to do. It uses Gauss genre, and there we go. Now that's 1D, and how about higher dimensions, so more variables? So the trouble with more than one dimension is that a whole bunch of things that work nicely in 1D no longer work here. First of all, the number of points that you need explodes radically, right? So if you have one dimension and you need 100 points, okay. Now you have 2 dimensions, you're going to need 10,000 points. 3 dimensions, 1,000,000 points, because with each dimension I'll need that grid. It's especially true if it's a regular grid. So if D is large, that's just not going to be feasible. It's not going to be very good. And so we'll need a way around that. Another thing that can be really troubling is that suppose you have a peak in the function, and that contributes a lot to this integral, right? Then it's very easy to miss that in 1D, but as we make the grid finer and finer, at some point we're going to hit that, right? Whereas in 3D, it's easier for this to sort of hide itself, because it's peaked in all kinds of directions, right? So it's easier to miss things, especially because you're going to try and reduce the number of points as much as you can to mitigate the first point. And then finally, the domain itself can be very complicated. So that's what this blob is supposed to show. This might be the area of integration, right? So in one dimension, all your domains of integration are between A and B, or maybe a couple of intervals that are AB and AB and AB. Here I have to describe what the boundary is of my domain. So that's an additional complication that you just don't have in one dimension. It's either an interval or it's nothing. Here it's some shape. So that makes 1D harder. Now, we can still try doing this sort of iterative approach if the number of dimensions is small. So maybe we have the luxury of computing 1 million points. It's actually not all that bad. And so for that, SciPy comes to the rescue once more with a routine called double quad, which does pretty much exactly what you'd expect. It takes a function of 2 variables and recursively basically evaluates the 1D integral, and then from that the 2D integral. But it has this option of describing the shape of your domain, and that makes the interface a little bit funny. So the function is simple in this case. We're trying to integrate x times y over a square interval where x goes from 0 to 3.14 and y goes from 0 to 3.14. And so the function is just defined as x times y. And then there's 2 extra functions I define, y1 and y2 here, which are the functions that give me the y limits. So, and it does that because although this is a nice square and pretty simple, in general, the shape of this 2D domain could be described by saying, well, as x is varying, what is my first point in the y direction and what's the last point? It still assumes that this is a coherent single domain, but so even in the case where you have constants, you have to define these functions. Say, okay, whatever x is, the lower limit is always 0. But in general, these lower limits could depend on x. That's this shape complication that I talked about. So you have to pass these functions y1 and y2 into the double quad function. Give it a, b, that's the x interval, and the functions that describe the y limits. And then it will compute whatever. It does the same kind of thing as quad. It's adaptive. You could say, you could put a limit to the number of points. You could say what the absolute or relative epsilon have to be, etc., etc. So this works well when your number of dimensions isn't too big. So in this case, it has to be 2. I wonder if there's a triple quad. I didn't check, but you could imagine that would be one. If the function is relatively smooth, because it's still a sort of a grid, even if it's not completely regular. If it's not very smooth, it's easy to miss peaks, etc. And yeah, and the function is fairly simple, so that if you're evaluating it, it's not too expensive. So this works well when it works, but there's a point or a number of dimensions where this is simply not going to work very well. So here's a case where it doesn't work well, where I have a fairly irregular case. And in those cases, we're going to go over to a method called Monte Carlo integration. So suppose that this is my domain, and say the function is just 1 on that and 0 outside, and I want to know what the total area is. If I take this regular grid, you can see all kinds of tentacles have been missed just by putting that regular grid on. And even reducing it by 1, it's still easy to miss stuff. And that's kind of funny, and it could just be an artifact, but who knows, maybe there are these arms that go exactly along a direction. See, we just don't know. This gets worse in more dimensions where it's easier to miss things, but I can't draw that as clearly. So instead of doing this regular grid where we miss features just because our grid walks along the line of that feature, if the feature is fairly regular, to get away from that, I can just move these points. I'm just going to randomly move them about. If I randomly move them about, it's going to be much less likely that I'm missing a feature. Right? There is a feature there. If it contributes, there's a decent chance that the point will be there. And if that point is not going to be there, if it's a random point, maybe the next point will be there. So shaking them up means that regular features aren't missed as easy. Random features would be missed, but then that's the next random point would not miss them, right? So there's the artifacts of this grid are no longer there. But you lose something when you do this, because a lot of points, well, basically you can't really guarantee coverage of the points that are important. Yes, there is a point here, but it's just one point, right? I might now have less points here and more points over here. What does that mean? Like, that means that my approximation here should be less accurate than there. So what you can show is that although you don't miss features as easily, your convergence, that is the number, how the number of points has to increase to get convergence, changes. So independent of how many dimensions you have, it basically goes as 1 over the square root of n. That's your error. So taking, if you want things to be twice as accurate, you have to have 4 times as many points. And this wasn't true in the regular Gaussian cases where things tend to go as 1 over n to some power, like 2 or 3. They converge really rapidly. So the convergence is not as fast, which is why you're not doing this typically for 1D or 2D or even sometimes 3D. But it's pretty much the only way to get anything done for higher dimensions. It's also fairly simple. Like, you don't have to know much. You just randomly throw these dots on and you see what the function is. And that's all you do. Now, I don't know if it's because it's so simple or because there are many different variations of this theme, but there's no single Monte Carlo integration package that I just say, okay, it's not a SciPy, so you can't just say, here's my function, just randomly start picking some points in the domain. So you probably do this yourself. There's some specialized packages that might fit your particular use case. You can look for it, or you might already be using them. But the essence is always the same. You take some random numbers, so you generate some random numbers, which give you random points. On those points, you evaluate a function, and then you average the value, and that's your integral. You can try and figure out the deviation by just saying, okay, what's the variation in my values? Or you can say, well, let me take more points and see what the difference is. So you can sort of estimate the convergence from that. So it's a very generic way, but there's this inherent uncertainty of even getting close to your answer means that oftentimes you sort of tweak this a bit. You might, and so suppose you have a function, you kind of know the important part is over here. I don't want to be sampling over there, but I also have to sample over here because it contributes, right? So maybe there's a big peak around 0. I want to say, well, look, especially around 0, around the origin. But I have no, like if I just draw them randomly, I'm not going to get that. So I'm going to have a lot of points wasted in areas that aren't important at all to me to just get the right answer. So there's ways to bias things. You can say, well, just sample mostly around here. And then that won't give you the right answer if you have too many points there. So the average will be wrong. So you have to sort of undo that bias. It's a nice way, sort of a important sampling where you take this is my important area. And it's very useful, but it's one extra step, and that's one reason why you don't really see generic MC functions. Like, wow. Other variations, and this is very common, especially in simulations of sorts, is to not have these points randomly generated, but to take one point and construct the next point by some sort of algorithm that is random. So it's like a random direction, like random steps. And depending on your problem, this could get better or worse coverage. So I could imagine doing that here and just taking steps. Here, that doesn't seem like a very good idea because it takes a lot of steps to get over there. But if you have sort of physical constraints of what the steps could be, doing this, so having those constraints built into your next step means that you're not sampling parts that are not important to you. So you can imagine having configurations of a molecule, and some like have 2 molecules. Having them right on top of each other is a very unlikely and unusual situation. You might want to move away from that. So if you take small steps, you could say, well, it's more likely to have them go away from each other than towards each other. That's a way where you can sort of tweak things. Again, this is very dependent on what your actual problem is. Again, but it's a very widely applicable technique, Monte Carlo, but it's also widely highly discipline specific or problem specific approach. So just a little intermezzo before we go on to the next topic of ordinary differential equations is about random numbers. We saw that we can find them from the stats, the SciPy stats package, but there's no such thing as truly random stuff. I don't know if we've stressed this enough, but the computer can compute random numbers, but it can't. It can't be random because if it computes it, it's deterministic, right? So you always have these pseudo-random numerators, number generators, and they're only as good as you want them to be, in a sense. You start from a seed and you generate numbers, and you hope that subsequent numbers are more or less look random. They're not random; they just look random. So you can do statistical tests on them to see if they're random. Something you should be done, and they're not all good. Right now, the good news is after decades of people using bad random number generators and the standard number generators in programming language being specifically bad, this is certainly true for languages like C, where people didn't really care about randomness because C wasn't written for scientific computing per se. A few very decent ones have become standard. One of them is called Mersenne Twister, and luckily Python is using that by default. However, and so Python is nice to you and says, okay, this is what I'm using. But having another one used, so if for some reason you want something even better or you want to experiment with that gets harder in Python. So if you're not quite sure whether your random number generator is good enough, one way to do it is take another one and see if it gives the same result. And so that turns out to be actually not as easy in Python as in some other languages. Now, I'm sure you can find non-standard Python packages that do this for you, so you can look around. I'm sure they are there. You could write your own if you want, but that's writing a good one your own by yourself is really, really difficult because you'd have to do all these tests. Picking a couple of ones, saying, okay, I've heard of this one, but how about this other one that people say is very good too? That's difficult. Okay, so that's just an intermezzo. But if you're doing Monte Carlo, Monte Carlo is only as good as your random number generator. So you do have to be able to know that they're good. Okay, so that was integration in a nutshell. 1D, 2D, it's in SciPy. Higher dimension, you're going to do Monte Carlo of some sorts. Questions? No. So one of the reasons that this is together with the topic of ordinary differential equations that we'll see they actually are related. So ordinary differential equations, or ODEs, are basically equations where there's only one variable that causes a derivative. In many cases, this is time. So an example is the Lotka-Volterra system, where there's a population of predators, I think that is Y, and of prey, which is X, and Y eats X. And there's not many predators, the prey thrive, etc. So these are this is sort of a simplified description of what happens, how populations grow or shrink with time, given the existing populations of predators and prey. So the exact values of alpha, beta, gamma, delta, the parameters here aren't so important, but this is one set of equations that in time shows you how these two populations interact. So it's an ecological model. But that's not the only case where ODEs occur. Gravity, the Earth, gets a pull from the sun, who also actually gets a pull back, can be described by ordinary differential equations. But in this case, they're second order, second derivative. So that's this square here, if you're not too familiar with that. So the second derivative of x, which is really the acceleration, x being the relative position between the sun and the Earth in the x direction, and y is the same in the y direction, is some sort of force, the force of gravity. And these things will turn out to move in ellipses, but that's the solution of these ODEs. In chemistry, you often find ODEs in rate equations. So these are concentrations of different reactants, K1, K2, etc., reaction rates, and this can be used to describe how a reaction moves about. It's actually not too different from the predator-prey model. In weather, or at least simplified models of the weather, like the Lorentz system, gives you some sort of description. This is a highly extracted system that is really only used to show that there is chaos in the weather system. At some point, X, Y, and Z meant things like pressure, temperature, but they really don't. But it is sort of this is the kind of features. There's no linearities in there that would describe weather. And even if we have this unrealistic model, we can't predict the weather at all after a certain time. And that's sort of the main point of it. But again, it's a system that is described by ordinary differential equations. What can't be done by ordinary differential equations is stuff that is sort of spatial. If you have your population, but you want to know where they are, what the concentration is at each point, you'd get what's called partial differential equation. You get derivative with respect to X and Y, the positions, as well as time. We're not talking about those here. We're talking about only one variable to which you take a derivative. Okay, so they occur in all kinds of fields, all kinds of modeling. And so if it's of any interest, you can probably not solve these exactly. Okay. So since they can't be solved exactly in general, what do we do? Well, we solve them numerically. So just as a general, last bit of generality, we can always write these equations as some linear combination of derivatives of a function y that we're after, with the right-hand side as some function of that derivative. In other words, I'm specifying, this should not be t, this should have been, or this should not have been x, it should have been t. So for any given t, if I know y and t, then I can get sort of the derivative, the direction in which things are moving. That's what this does. But it could be an acceleration, it could be a velocity, depending on the order n of the equation. Now, and we'll start this thing off with some given acceleration or some given velocity at time 0 or time t0, whatever you want. So we have our equation, we have an initial condition, and we want to see where things are going. You could also imagine that we want to know we want to specify how things are now and how they're going to be in 100 years, and then figure out what happened in between. So sort of boundary conditions. That's a very different case. I'm not going to talk about that right now. So we're going to do just initial conditions where we know okay, things are this way. I have equations that govern the time evolution, and let's see what happens. Now, the nice thing about
is that a Taylor expansion on top?
Not necessarily, no.
Okay.
It's just there's any n order up to n. So the one we want to look at only is n equals 1, where we just have a single derivative. And the way we can do that is that we can always treat the derivative of nth order as the first derivative of the n-1th order, and call that n-1th order the new variable. So for instance, if I wanted to know something second order, I could define a new function called y1 that is just the derivative and say, well, its derivative is equal to y1. So I can convert any order equation to a set of first order equations. I only really mention that because next I only want to look at first order equations, but I have to look at them where they can have more than one component. So for instance, just going back to these examples, these are already first order with 3 components. But to turn this into a first order set, I can do that, but I'll get 4 equations. I'll get x, and I'll get the derivative of x, which is the velocity, I'll get y, and the derivative of y. So I just get twice or 3 times the number of variables, but it's still just a set of ordinary differential equation of first order. And so that's all. Since we can always do that, you'll find that all the numerical recipes that are out there for you will just use the first order form. That means that when you don't have a first order form, it's up to you to transform it in that form. So let's assume that that's been done, and we'll start from the general first order form. So y is our function that we want to know. F is basically the direction things are going if y is a certain value, and they can depend on time explicitly too, although I'm not going to look at that too much. Okay. So if that's our equation, and we know our initial y, and we'll assume that y can have multiple components, but it really doesn't matter to write them down explicitly. How are we going to go about this? Well, with a bit of algebra, we could try and take a step h in the future and write this in an integral form. And I'm just mentioning this because it shows that the idea of integration and of evaluating an integral and computing the solution of an ODE are very related. The same kind of idea. We want to go a step h further. We can't have every point because there's an infinite number of points in the future. And so we'll have discrete points. And so we want to basically approximate this integral. And we've just been approximating integrals. So we'll do a similar thing, right? We'll try and maybe have some intermediate points or have 2 points and approximate this integral and see how well this goes. There might be a convergence, there might be an adaptive size between the steps, just as we could have adaptive number of points. But that's kind of where the analogy stops. So it's a discretization. You have a finite number of time points. You'll select them such that your accuracy is a certain level. But there's one thing where things are different, is that the answer that I'm after is y, but it occurs in the integral. Right? So we have to come up with something a little bit different. So let's look at a few simple ways to solve this and to see how we get around that problem of having that. Oh, and then just before we do that, let me mention that there's this concept of stiff ordinary differential equations, which has no, you'll hear it. You have an ordinary differential equation to solve, and somebody might ask, oh, is it a stiff ODE? And you can't answer that question really, because there's no formal definition of stiff, except it's hard to solve by numerical means. What often happens is that to solve it, you would need a ridiculously small time step. Because there's some part of your equation that evolves really, really quickly. So to resolve that, you need a small time step. But what you're after is a long time step. So imagine you want, oh, let's just keep it at that. So there are certain techniques that really perform poorly when you have this kind of a situation. So they can't handle stiff ODEs. And there are some that try to accommodate this a little bit. If you're using a method, read its documentation, and if it mentions that it's good for stiff ODEs, then good. You typically don't care until you find out that you have difficulties. Okay, so let's go a bit back to basics and keep it simpler. Here's my equation that I want to solve, and I want to go a step in time. Let h be this step in time, right? So it's tn minus tn plus 1 or something like that. So h is my time difference. If this is the direction in which y is moving, then at time h later, y should be h times that direction, right? This is the slope, and h further, that's my new step. It's actually a simple approximation. It's a valid approximation. If h is not too big, that's exactly what should happen. And in fact, if h gets smaller, the approximation becomes better and better. So this is a scheme called forward Euler. Euler invented it, and then it kind of showed right away why nobody should ever use it, which I'll show you too. But it's a valid approximation scheme in the sense that if you did a Taylor expansion of your variables, so that's expanding around a point and using all the derivatives at that point, you would find that the error you make by doing that is of the order of h squared. So if h becomes twice as small, my error is 4 times smaller. Great, right? So it seems like you have a handle. You just take small steps, and if it's not small enough, you take smaller steps, and you get closer and closer to the answer. So one calls this order h squared so if you're not familiar with the order symbol, it just means something proportional to h squared. So this is called the local error. Local because I'm making it every step. I'm not going to take just one step, because then I only get h far, and I want to get a whole century ahead or something like that. So for a given interval, I actually need, if my step size were fixed, the t1 minus t1, t2 minus t1 over h steps. So that actually grows. The number of steps grows as I make h smaller, which means I actually get n times that error, potentially, leading to an error that is actually, because n is, it goes as 1 over h, is of order h. So this is called the global error. So I have a nice approximation scheme that gives me order h squared, but in reality, the error is not going to be any better than order h. So that is not very accurate, but it still seems like, okay, I can still make h smaller and eventually get something. Unfortunately, what turns out to be the case is that this is not a stable scheme, and I'll show you what I mean by that. But it's not the accuracy that makes it unusable, because you could take smaller time steps and eventually get there. It's the stability that really kills you here. So let's look at this predator-prey system once more. Here are the equations again. X was the prey, Y are the predators. Let's take some parameters. These just work out to be nice in the sense that it gives you, these are things like birth rates, how hungry the predators are, etc., or how good they are at capturing prey. And some initial points. So let's say we have 60 preys and 120 predators, and we just choose a time step of 1/2. Kind of random, but it seems to work for 1400 time units, whatever the time units are, days or something. This is what I get. So this point 60 to 120 is in the middle here. And what happens first is that it seems like the number of predators is increasing. So they're eating their prey and you know, multiplying. And but then at some point, I guess they eat too much of the prey to sustain that, and the number of predators decreases until the number of predators has decreased so much that the prey can thrive again. And then at some point, the whole thing happens again, where, okay, now I have a lot of prey, the predators eat them like crazy, they multiply, they increase. So you get a cyclical behavior. But there's one thing that's kind of peculiar here, is that with every cycle, I get more prey and predators, right? So it's like I have an ecological system. It's supposed to be more or less closed, and the number of individuals of any kind is just slowly increasing. That seems rather unrealistic, right? That's, unless I keep adding more food to the, right? But that's not supposed to be in there. So either the model is really wrong, because that's not supposed to happen, or our numerical scheme is wrong. And it turns out in this case that our numerical scheme is wrong. What should happen is that these are actually nice cycles. It's not too hard to prove mathematically that every solution should just be a cycle. So it comes back to itself, and that's certainly not the case. So what this points at is this is unstable, and you can try different ages, and then eventually they all spiral out. It doesn't get any better. So we're making some sort of error here in doing this. It's not stable. So one of the things that we did, well, let's just go back for a second, is that we made this approximation here, right? By saying, okay, we're going to try and compute f at our previous time and compute a new time. That's kind of asymmetric in time. Like from the point of view of the approximation, it doesn't really matter whether this is time n or time n plus 1, right? I could imagine going back in time and making the sort of equivalent but reverse approximation where this is tn minus 1. And so what would happen then, rather than spiraling out, would be spiraling in if I took the opposite direction in time. So maybe if we go exactly in the midpoint of time, things balance out. Well, we could try it. So this is just a different approximation. You can think of it that way, and we're just going to try it and see what the consequences are. So that's how I'm going to approach it here, but that's the idea, a better approximation. So rather than saying I'm taking point yn, I'm going to take the next point and then average. So I'm going to say, okay, I know my function is here, so that's my slope, but really I'm going to look at the slope in the midpoint and then sort of get away from this drift. That causes a problem now, though, because I have to solve yn from an equation that has yn. So this is something that I have to solve in some sort of numerical way to find a yn plus 1 that satisfies this equation. So this is called an implicit formula. And so that sounds annoying, and it's true, but they have a very, really nice property of being stable in most cases. So here's what I did. I did this for the loss Volterra same situation and the same scale of the plot, just to show you the difference. Started at the same point, went around, and came right back where it should be. This is the numerical solution, and no more spiraling, nice and stable. I can actually crank up H quite highly before any errors, any instability occurs. So it really kind of happens because you can only have drift if there's an asymmetry in your time, and we kind of undid that doing this. So there's a whole slew of similar approaches. They all do the same kind of thing. They compute extra points or intermediate points and then see how things go. So I'm not going to go over this too much, but there's some names here that you might see come by, and that's fine. Once more, you want to use adaptive stuff here, right? So your time step probably shouldn't be constant, because what you want is to see that your solution is accurate up to a certain tolerance, not whatever happens. So you want to be sure of your error. So you can compute your error, for instance, by taking a step size h and take another step size h/2 and see if they're of similar magnitude. So that's an adaptive method. And what will happen typically is that as your integration proceeds, in other words, as your solution proceeds, the time step will vary. And that's fine, that's good. Just such that your solution is equally accurate along the way. So there's a couple of packages that do this. ODE int in Python, obviously, and ODE. I think I have one. So here's an example of using ODE. So there is in SciPy integrate. So ODE int is, you call it with the system being, I give it Z, so Z is the point. So it's the equivalent of Y, I don't know why I call it Z here. And a possible time, and it computes the right-hand side, essentially, of your equation. So these are the right-hand sides. Here they are in terms of Python, and it returns the list of those two as a list, or anything that is two components. I can take a linear space of time points that I want my solution at. That's not necessarily all the points it uses. It might use more points if that makes it more accurate. But this is where it's going to give me the results back. So I give it the system, the initial condition, and the time. That's great. And it'll do this adaptive step kind of stuff and give me the solution back. Solution will have two components, x and y, so I extract them and plot them. And this is the initial conditions and alpha, beta, gamma, delta values are different here. But okay, so that's a lot of theory for just using this, but I just want you to know what's happening here, that it's evaluating your functions at more than just time, just the times that it needs to give you an accuracy. You can give this accuracy arguments as well. And sort of why you use this and not invent your own, or why you don't just implement Euler, because you'd get off conclusions. So, quickly, just we talked about all of these. SciPy integrate for integrating things, ODE int for integrating ODEs. They're good safe bets, right? But they do sort of lock you into one particular method. That's fine if you just if it fits for your method. There are cases where you might have to go beyond, but okay. So, any questions about the ODE stuff? Okay. Now I have a question. What do you guys want to see next time? So last year we did partial differential equations in the last lecture. And if that's something you are using, so you have some sort of diffusive part to your equations, or that's great. But you might want to look at something else. One thing that I thought I could also touch upon is a package called Pandas, which is sort of it deals with tables, but sort of in a very data sensitive way. Data manipulation analysis becomes much easier than you would do in, say, Excel. But it still has sort of a table based, and it's kind of nice. So I'm going to ask you to choose between these two. You can either talk about partial differential equations, which will be easy in the sense that I already have the slides, or something new which you might like and which will teach me a little bit more as well. And I've used it, but teaching is the best way of learning something. So I'll want to see hands for partial differential equations. Hands for pandas. See, I had a suspicion that might happen. So next time, pandas.